Okay, and we're recording. Okay, so here's where we were last time. Welcome back, everybody. Sorry, I forgot my mask. Last time we talked about section 1.6, got that done, and we're now going to, I hope and expect, based on what happened in this morning's section, we're going to finish 1.1 and 1.2 and 1.3 all today, because they're mostly review. It's mostly stuff that y'all have seen before, I hope, in linear algebra class. I'm going to, as usual, I'm going to be focusing on the parts that either you haven't seen or that I think are most important for review, thus leaving to y'all to read for yourselves the review items that I think you can review for yourselves, and I think you'll be fine, or possibly things you haven't seen but that are very readable and that you can just take a look at. So as usual, I will be trying to make the best choices of what's going to be the best use of class time. Okay. All right. So 1.1, there's very little left for me to say. I do like to quibble about the book's notation. They use bold as their sort of supplemental indication that what they're talking about is a vector. That's nice in print. But the problem is, if you're writing with a pen or a pencil, as we are, then bold means you have to sit there and go over it several times. It's very inconvenient to write in handwriting. So I like this vector hat notation that I'm sure you all have seen before in your linear algebra classes, because if you're doing it with a pen, it's straightforward to write it. So anyway, heads up, the book will be doing it the bold way probably, and I'll be doing it with the vector hat way. The other little quibble that I'll mention is for a vector like this. The book is writing it as with this notation here, P1, P2. Well, that's fine. It's perfectly unambiguous what they mean by that, so that's, no problem. On the other hand, it is also P2 minus P1, keeping in mind that each of those points, right, is also can be thought of as a vector. And that when you subtract those two corresponding vectors, you do get this green vector. So what we've got then is kind of a trade-off, and which one of these do you like better? I like this one because it shows the algebra that's implicit in what we're looking at here. Right? So specifically, the fact that this arrow goes from this point to that point, probably not as useful as the fact that this vector that we're talking about can be thought of as algebraically related to two other things. Algebra is useful, right? So in vast majority of cases, I'm going to write it like this because I think it's more transparent and more useful notation. It's just a personal preference. There's nothing wrong with the way the book is doing it, but I just wanted to clarify why you're going to see different things from me than from the book. Okay, so that's section 1.1. Correction, that is the part of section 1.1 that I think is, that is worth class time. Okay. Make sure to review all the rest of it. Make sure to read all the rest of it, etc. Okay, so 1.2. There's more stuff about vectors, again, a lot of which you've seen. What you probably haven't, or what you very likely haven't, is what a parameterization is. So I want to spend a bunch of time talking about parameterizations. A parameterization is a function. Specifically, it gives you position in space as a function of a single parameter. And, so in general, this can be any parameter. Now, that said, most of the time, we'll call it t, and then we'll think of that as representing time. So in most cases, when you're parameterizing a curve, you think of it as position as a function of time. So in some sense, you can think of it then as that a parameterization, if you think about position as a function of time, that's the process of drawing the curve. Because when you draw, if you take your pencil and you trace something out, that at any given time, your pencil is at a certain position. Right? So such a function you can think of as literally describing the process of drawing the curve. Okay, so let me give you an example, see what these look like. Here we go. We have position, x comma y. They're x and y are given as functions of time, and specifically x is this function of time, it's cosine t. Y is this function of time, it's sine t. Before I go on, I do want to point out something about notation. You may notice here that for the vector x comma y, I'm giving this the name x. Right, you see it right there. I'm using x vector to indicate x comma y. I just find that to be convenient. I suppose I could have called it other things. It does seem a little unfair. After all, the letter here is this letter, not that letter. But, I had to pick one. X comes first. Doesn't really matter. Anyway. Okay. So we have position as a function of time. And the question is, this, if it's drawing out some curve, what curve is it drawing? Okay, well, the easy observation to make here is that x, being as it is cosine t, and y, being as it is sine t, and keeping in mind that we know the Pythagorean trig identities, right? Sine squared plus cosine squared is 1. That means that these x and y satisfy this relation, x squared plus y squared is 1. And we know what this is, right? This is a circle. So what that means is that this parametric curve, every point that comes out of this parametric curve satisfies this equation, and therefore every point on this parametric curve is on the circle, which strongly suggests that it's actually tracing the full circle. Now, to be fair, we don't know that it's actually tracing the full circle, but it's easily seen to be true because we can actually just kind of start drawing and see what happens. Now again, our circle, I'll draw here in purple. And now let's look at these points coming out of the parameterization. We know that every one of these points is on that purple circle. Start plugging in values. Let's plug in t equals 0. At t equals 0, you get this point right there. And then let's plug in a slightly positive value of t. 0.1 or something like that. Slightly positive value, you're going to get a little bit less than 1 for the x coordinate, a little bit more than 1 for the y, a little bit more than 0, for the y coordinate. That'll put you somewhere along in here. And as t increases, I think you can see you're just going to be moving around the circle. So from t equals 0 to t equals 2 pi, you trace out the entire circle. Okay. All right. Now, this is how we analyze this parameterization. The thing about it is they're all different. So it's not always going to be as simple as that you can look at the formulas for x and y and just, let's see, do I remember any convenient relations between them, and then just sort of take it from there. Sometimes that works. This is a great example of that. There are other methods that you'll use in other cases. Now, what I'm going to do is I'm going to show you a few more examples of ways that you can analyze parametric curves. And the methods work sometimes, and each one of those methods you should think of as a tool. It's kind of like a tool in a toolbox. And sometimes screwdrivers are useful, sometimes they're not. Sometimes hammers are useful, sometimes they're not. It's nice, though, to have a toolbox full of tools. And then use the appropriate tool in the appropriate circumstance. Okay, so here's the next example. So what do we got here? There's a parameterization. What is it? Well, keep in mind, that's x, and that's y. Right? After all, the parameterization, make sure to remember, gives position, x comma y, as a function of time. Okay, so first thing we're going to do, notice that I can solve for t in this first equation. Solve for t. If x is equal to t minus 1, then t is equal to x plus 1. I can take that formula for t and I can plug it into there. That's just plugging in. T equals x plus 1, as previously solved for. And notice what I get then is I've effectively eliminated t, and I get that y is equal to 3x plus 7. And so this is an equation, and now furthermore, more importantly, this is an equation we recognize, right? And so, well, yeah, it's a line, and therefore this parameterizes a line. Now, sometimes this is handy, right? Sometimes it's easy to solve for t and easy to plug it in. Full recognition. Sometimes it's impossible to solve for t, and at which point this is not a useful method. But, again, tools in your toolbox. Okay. All right, now let me show you a different way to analyze this same question. First, recognize that we have a formula for x. Recognize that we have a formula for y, both in terms of t. And rather than solving for t, I can instead ask, what do I have to do to this expression to make it look more like this expression? And, well, it's not that hard of a puzzle. You see I've got a t here, I've got a 3t there, so how about I multiply both sides by 3? Now you got to be fair. You got to multiply both sides by 3, right? But now what do I have to? Well, now I have to add 7 to both sides, and altogether, then, in the process of algebraically turning that into that, notice I end up with the same equation of the line that I had before. Now, it's a different method to get to the same conclusion. Again, different tool for your toolbox. If you can't solve for t, notice here you didn't have to. So sometimes this will be a more useful method. Let me pause. How are we doing? Is everybody on board? Everybody with me? Yes?
Is the goal to get it in like terms of x and y?
I mean, the goal is to get it into some form where you recognize and where you can say, oh, I know what that is, right? So, yeah, very often, I mean, we've all had extensive high school algebra courses, and typically if you have an equation, that's going to be something probably going to be more familiar. But the goal, to be precise, is just to get it into some form where you recognize and can say, oh, I understand what that is. Yep, it's a good question. Anybody else? Everybody happy? Let me show you the next example. This next one's in 3 dimensions. So this is a little bit harder example. Keep in mind, position in 3 dimensions is described by an x-coordinate, a y-coordinate, and a z-coordinate. So I've got x, y, and z as functions of time. Yeah, parameter. Let's think of it as time. Why not? So if you try to find a single equation, play around with the algebra of these, come up with some single equation that involves all 3 of the variables and that conclusively tells you what you have, you're going to fail. It's not going to work. What works out better in this case, and again, every case is different, tools in the toolbox and all that, is to kind of break it down into parts. Right? And first thing I want to do is let's look at the projection into the xy plane. So I say this is the projection into the xy plane because I'm ignoring the z-coordinate. If you think about it, if you throw away the z-coordinate, what you're doing is you're just kind of dropping, whatever point you're at, you're just kind of dropping straight down into the xy plane, below it, as it were. Okay. So if you project down to the xy plane, well, good news. We recognize that. Cosine sine. We've seen that one before. By the way, this is a really good one to have memorized, that this parameterizes the unit circle. Very convenient. Comes up a lot. So go ahead and have that one, on the tip of your tongue. So, cool. So what this tells us, it does not tell us what the curve is. What it tells us is that the projection down into the xy plane is a circle. So I don't really know what's going on in the z direction yet. We haven't thought about that. But if you were looking at it from above, if you're looking at the shadow down in the xy plane, the shadow is doing this, moving around in a circle. Everybody okay with that? Okay. All right. Now here's the other thing we can do. we can look at the projection to the z-axis. The projection to the z-axis says, forget about x and y, let's look just at the z-coordinate. Well, there it is. So that's the projection to the z-axis. And the projection to the z-axis is actually pretty simple. I mean, z is just t. So as time passes, what we've got is our curve is above this shadow, and this is a hard coordination problem, so I hope I can do this. It's above this shadow going around like this, and then rising at a constant rate. It's hard. Going around in a circle and rising at a constant rate. And if you kind of think that through, right, I think you can persuade yourself that it is doing like this, namely that shape that I have drawn there, which, side note, is called a helix. And I imagine you've probably heard that term before. It's like a spring. What do you think? Seem plausible? A little bit of geometric intuition there that you have to kind of, when you combine these projections. Okay. All right. So notice this is a different way of breaking things down, different tool for your toolbox. Okay. Next thing I want to talk about with parameterizations is what if you want to go the other way? Now, what we've done so far is I've given you the parameterization and I've asked what is the curve that function describes. Now we're going to go the other way and I'm going to say, suppose you know the curve and you want to know what is the function that parameterizes it. What is the function that is the parameterization, and so that we're turning that into a verb. We talk about parametrizing a curve. Okay, so again, various different methods. My favorite, you'll see why in a moment, it's called the graph parameterization. It's a wonderfully powerful and convenient trick. It'll work with any curve that is a graph, which means that you can solve for one of the variables as a function of the others. All right, so this is, by the way, we're going to spend more time talking about graphs and what precisely is a graph, etc. But the big punchline is going to be that one of the variables is a function of the others. In this case, only one other, because it's two-dimensional. Okay, if that's the case, here's the big trick. The big secret magic trick for graph parameterization is let your parameter be the input variable. That's it. Everything else will just fall into place. Let the parameter be the input variable. Let's see one. Okay, here's a graph. That's a graph because I've solved for y. Y is given explicitly here as a function of the other variable x, as so. All right, so now I'm just going to follow the instructions. It says let t be the input variable. Okay, the input variable is x, so I'm going to let x equal to t. And I claim everything's just going to work now. And here's how. If, after all, x is equal to t, well, think about it. If x is equal to t, that pretty much forces then that y has to be t squared. Right? Because x is t. You plug in t there, and you get t squared. And we're done. We win. Victory. X position is a function of t. Parameterization. Everybody see how that worked? And hopefully you can also see this is always going to work, right? Whatever, if one of the variables is solved for, just let t be the other one, plug it in, it's going to work. So awesome trick, very powerful trick for creating parameterizations. So make sure to memorize, make sure to be really, really comfortable with this one. Now, I don't want to say this always works. It doesn't. There's plenty of examples of curves that are not graphs. And there's other examples of curves which, yeah, they are graphs, but there's better ways to parameterize them. So this is not good enough as an only method. It's a really good one. very often. Okay. All right. How would we do this example here? That's not written as a graph. This is not written as one of the variables is equal to a function of the others. But it could be, right? We can take that, we can just choose to rewrite it by solving for x. Easy to solve for x. Now, I indeed have one of the variables as a function of the others. And I'm going to follow the same rule as before. The input variable, in this case y, I'm going to let it be the parameter. And then when you plug that in, that tells you exactly what x has to be. X has to be that. And we win. We have a parameterization. There you go. X and y functions of t. There's nothing magic about it being y. That's the variable that you've solved for. You can go the other way around. Same basic idea. How we doing? Is everybody happy? Okay. Good deal. Okay. All right. Now here's another example. This is a fundamentally different method. This is an example, by the way. I already kind of hinted at this. Sometimes the curve you're interested in is technically a graph, but you don't want to do it that way. So this is going to be a great example of that. What we have here is a wheel, and on that wheel, radius A, on that wheel we have a reflector. And as this wheel rolls, and I'm having it roll to the right, you see, kind of use your imagination for your physical imagination. Pretend this is a bicycle, for example. Right? As that wheel rolls to the right, that reflector is going to, you've probably all seen reflectors of bicycles going down the street, and they do this kind of thing, right? Make a kind of a pattern like that. So what we want to do is we want to parameterize that curve, that wacky, weird curve of the reflector. All right? Technically, this is a graph because this passes the vertical line test, and so, technically, I could view y as being a function of x. You don't want to do it that way. It's super hard. Okay. All right, so here's what we're going to do. We're going to use this method. Method's a strong term. We're going to use this general strategy of try to use vector algebra. Let vector algebra turn a hard problem into two easy problems. Sometimes difficulty is not conserved. Right? So looking at this reflector by itself is a really hard problem, but we're going to break it down into a sum of two vectors that are both easy, really easy. A couple of details to worry about, but way easier in parts than they are as a whole. So in particular then, notice that the location of the reflector, let's see here, let me do it with the colors. The location of the reflector there, I can break that down as, it's the location of the axle of the wheel, which I'm calling A, plus, let's see, I'll use green here, plus this difference there. So blue plus green gives me the reflector. Everybody believe it? I claim parametrizing that blue curve is going to be easy. Parametrizing that green curve is going to be easy. And then we'll just literally add them. Now, that remains to be seen that they are in fact easy. We'll go through all those details. Okay, next thing we have to do before we get going on that, we need to decide what our parameter is going to be, and this is something you don't want to be sloppy about. You want to be very, very careful, very crisp and clear, and how you indicate, even to yourself, right? Be very clear to yourself, but also, of course, to your reader. What is your parameter that you're using? I'm going to make the choice here for my parameter. Maybe I'll give some justification for it as we go along. I'm going to choose as my parameter this angle here, T. And let me tell you what I like about this as a parameter for my parametric curve. I could have chosen, distance that we've rolled, or I could have chosen, time, elapsed time. If I chose time, now I need to know the velocity. I don't want to deal with, there's no need to invoke velocity here. The curve I'm trying to parameterize is the same no matter how fast the wheel is rolling. So I don't want to bring in speed. So I like the idea of an angle instead of time. Angles are convenient because if you look at this D vector, right, that D vector going around in a circle like this, cosines and sines of an angle. So angles are going to be a convenient sort of foot in the door. The other thing that I like about T is, if you think over here to this, to our initial state, in our initial state, the reflector is straight down, right? And the angle being as it is measured off of the straight down direction, we're starting here where this parameter T, as I have defined it, is 0. And starting at T equals 0 is, I'm going to say, appealing. It's not required, but it's nice. It's intuitive. The other thing I like about it, one last thing before we go on. This angle T, as I have it described here, note the picture. Okay? As the wheel rolls, T is increasing. That's good. Right? As time passes, I want the wheel to be rolling the correct direction. If I were to do this differently, if I were to define, let's say, and I'm not going to do this, but let's suppose I had defined T to be that angle. Then notice as the wheel turns, that angle decreases. Or said differently, as that angle increases, the wheel's rolling backwards. This is confusing. Right? So unnatural, so we're not going to do it that way. So I think this is a pretty good choice for our parameter, T. Okay, so let's make use of it now. Let's start with the axle. Here's the axle. There it is, right there. How can I write down a formula for the axle? Notice that the y-coordinate, of course, is just A, because this is a wheel of radius A, so the axle's A off of the ground there, and so the y-coordinate's A. That's the easy part. For the other part, the x-coordinate, it's this distance. And notice that distance is the amount of road that the wheel has covered since the beginning point. And here's the real tricky little bit. The amount of road that the wheel has covered, the amount of road that has touched rubber has to equal to the amount of rubber that has touched road. Now that's a physical appeal. You got to think about when something's rolling along, right? If a wheel has a certain circumference, then when it rolls around one turn, the distance it will have covered is one circumference, right? Otherwise, it's slipping. Right? So I think that's a pretty reasonable pitch. What do y'all think about that? Okay. So the x-coordinate that we're looking for is equal to this purple arc length. And now I remind you of your old high school geometry, and arc lengths are radius times angle. The radius is A, the angle is T, so that arc length, therefore our x-coordinate is AT. What do you think? Everybody good? All right. It's a slick move. By the way, I mean, I want to point out that the reason that I know how to do this example is because somebody told me. Somebody showed me this clever thinking, right? I did not dream this up, this idea of rubber equals road. This was an observation that was made to me. I was probably about where you are. And so you get to benefit in the same way that I did. And don't ask yourself, would I have been able to dream this up on my own? That's a much higher bar, and that's not what's expected. Okay. All right, next question. We want to look at this D vector. That D vector there. It's going around in a circle. Very important point. Make sure to remember vectors have direction and magnitude. They don't have a location. So I drew it over there because, well, that's where I happen to sort of have use for it. But that, as a direction and a magnitude, is this. And it's easier to understand vectors when we think about them in standard position. Right? So this is the thing I want to sort of parameterize, and I want to understand, as time passes, as t increases, I want to know where this green point is. Now, we're going to switch gears here a little bit. And let's think about how I would find out, how would I understand this point? And that's a point on a circle, and we typically understand points on a circle by you look at the usual angle theta, and cosine theta, sine theta, and don't forget the radius to multiply by. But the point is we use that angle theta. And here's where a lot of students make a mistake. A lot of students a lot of students make the mistake of being a little ambiguous about what their parameter is and exactly where on the picture is their parameter. So very importantly, t is this. That's not the same as, of course, this. Right? So seeing them both crisply on the picture, though, what you can see, and I think this is a pretty easy pitch, is that as t increases, theta decreases. And in fact, they always add up to 3 pi. 3 pi over 2. Right? So since they always add up to 3 pi over 2, we get this easy formula for theta. We already decided that the d vector is that. Again, very easily written in terms of thetas, cosine theta, sine theta. And we take this formula for theta in terms of t. We plug that in, and then we use our angle addition formulas. I hope you all remember your angle addition formulas from trig class. I know it was a long time ago. I know a lot of high school teachers kind of let that slide. For FYI, they're really useful and important, and we need you to know them. So make sure to memorize, if you haven't already, make sure to memorize the angle addition formulas for sine and cosine. Don't worry about tangent and cotangent and stuff. Sine and cosine, you do need to know the angle addition formulas. So anyway, plugging in the angle addition formulas, you can rewrite the d vector like that. And it's all over. We're done. We had, let's see here, this formula for A. We now have this formula for D. And we've previously agreed that the location of the reflector is A plus D. So, boom. Parameterized. And notice that now, of course, there's details involved, right? Of course. Definitely details. But big picture, I mean, the formula for the axle was just a matter of realizing that rubber equals road and writing it down and being careful, right? And D, pretty straightforward observation, and it's just a circle running around in a circle and just being careful about what the angles are. So each of these problems, the blue problem and the green problem individually, they're just things to know and a couple of little details, but fairly straightforward. The purple problem on its own, again, the actual, this wacky curve right there, without breaking it up into parts, would be a really, really hard problem. Yes?
Can you explain how the y-coordinate of the axle coordinate is?
Yeah, sure. So that is, I'm going to come back up here. The y-coordinate, keep in mind the y-coordinate is the sort of the height. And, well, the point is this wheel has a radius of A, and so that height's just going to be A. Yeah. Is that cool? Yeah. Yeah, no worries. Okay. All right. So, how often is it that you're going to need to take your curve that you're parameterizing and break it down into vectors? Well, it's a good tool for your toolbox. Plenty often enough to make sure that you're comfortable with this strategy. But it's, again, not the only method. Sometimes you can use a graph parameterization. Sometimes you can use another method. Okay, here's another example. Parameterizing a line. If you were to draw the vectors corresponding to points on this line, those vectors, you can see the direction varies, the magnitude varies. If you think of them as vectors, well, it's kind of hard. But you can break the locations of those points down, again, using vector algebra, because this point here, the given point that I know my line moves through, easy to describe. It's fixed, constant, and given. And these other vectors that I need to add to get to my points on my line, they're all parallel to the given direction vector. So if you're given a blue point and a orange direction vector, and someone says, hey, parameterize the line that goes through that point parallel to that orange vector, well, I just need to take the blue vector and add anything at all parallel to the given direction vector. And so that breaks down like this. TV represents vectors that are parallel to V. And for any value of t, you therefore get a point on that line. This parameterizes that line. So, so these purple points parameterized like so. Everybody good? So again, this you could view this as vector algebra, breaking down this point as a sum of blue plus green. That was the foot in the door that turned the problem into two easy problems. Okay. Alrighty. I think this is the last one I'm going to anyway, this is let's just say there's another one. I don't want to get ahead of myself. Sometimes you have an existing parameterization that you already know how to do, and to parameterize what you want, you just need to deform your existing parameterization. Just tweak your existing parameterization a little bit to get your new one that you're actually interested in. So, all right, in this case, suppose you want to parameterize this ellipse with, that equation. Which, of course, y'all remember your algebra 2. That's an ellipse that looks kind of like this. How do you parameterize that? So here's the thing. We already have an existing parameterization. We know how to parameterize the unit circle. Right? Easy. First one we looked at, cosine sine. And if you parameterize the unit circle, notice the thing we want to parameterize, this ellipse, ellipses are what you get when you stretch out circles appropriately. This circle has radius 1. The ellipse in the x direction needs to be 3 times wider than that. So all I'm going to do, I'm going to take my existing parameterization. I need to stretch in the x direction by a factor of 3. And so I'll do that by just literally multiplying all the x coordinates by 3. And then I need likewise to stretch in the y direction by a factor of 2. So I do that by literally just multiplying the y coordinates by 2. So we started off with this purple parameterization, which, again, that's existing, we already knew. And see that, this green question is really just a tweak of it. So tweak it accordingly, and there you go. So this here then parameterizes the ellipse. How are we doing? Alrighty, okay, let's see, let me just get ahead of myself a little bit here. Oh gosh, there are several more things we need to do. Wow. Okay, so I'm going to go through this example a little bit more quickly than I wish I had more time. But so you do want to be careful about the difference between parameterizations and equations. Both of them are algebra that describe a curve, but they do so in different ways. A parameterization generates points. The points on the curve literally are what come out of the function. Right? Position is a function of time. That means that the positions are the outputs. That's not what an equation is. An equation is what I like to call a point tester. It's a yay or a nay. You put the point into the equation, and if the equation works, then it's on the curve. And if the equation fails, then no, it's not on the curve. Right? It's literally a tester by whether the equation either works or doesn't work. So very different in terms of how algebra is used to describe a curve. And being sort of conscious about this distinction allows us to get clever with solving problems in some cases, and this is a nice example of that, which is, here you go, we've got, here's a parametric curve, and I want to know which of those points, this wacky parametric curve, I don't know, it looks parabolic maybe, I don't know, hard to tell, it's a pretty weird looking curve, but that parabolic curve, how does that, or does it intersect this plane? How would you do that? And the big idea then is to keep in mind that this generates points and this tests points. So we are literally going to, colors. We are going to generate points. There's our parameterization. We're going to take those generated points and we're going to test them by plugging into the equation. That's how the Legos fit together in this case. Parameterization generates points. We test to see if they're on the plane or not. And then notice that what that gives you is this equation, which you could just solve. And it's just a little bit of algebra. It's not that bad to solve that. And this gives you certain values of t. Now, let's not spike the football on the 2-yard line. Those are values of t. Those are the values of t that work. That wasn't the question. The question was, what are the points? Well, just don't forget, the points are what you get when you plug into the parameterization. So once you've solved for these appropriate values of t, you got to plug those into the parameterization. That'll tell you what the actual points are. And now you spike the football. Is that good? Okay. All right. Okay. Here's a parametric line. Again, the parametric lines, parameterizations in general, are point generators. What if you have a line in R3 given as a point generator, given as a parameterization? But what if you don't want what if you want a tester? It's tempting to say, what if you want the equation of that line? There isn't actually going to be a single equation, but in the spirit of an equation, what if I've got a bunch of points and I want to test them? Notice the parameterization is not good for that, right? If I've got here's an actual point. I don't care about all these other points. Here's an actual point. I want to know this point. Is it on this line? All I can do here is spit out other points on the line. It doesn't help me directly, right? So how do you turn a point generator into a point tester? And the big idea is, a way that you can test is literally to say, terminology I have to clarify. Don't forget this notation here means there exists. And one other little bit of notation, this thing right here means such that or so that. So arguably a test is there a value of t such that the parameterization spits out the point you're interested in? I mean, that'd be one way to say it. It's not very helpful. But that'd be one way to say it. It becomes a lot easier, though, when you take the 3 equations of this parameterization, and in those equations you solve for t. Solve for t in all 3 of those equations. You get 3 different formulas, of course. That's what the t you get from the green equation. That's from the blue equation. That's from the orange equation. Now let's ask the question, is there a value of t that makes all 3 of these equations work? And I appeal that, look, if t is going to make all 3 of these equations work, then these 3 things all have to equal to each other. Because t has to equal to all of them, how could a t equal to all of them unless they're all equal to each other? And so this is your point tester. The point tester is, are these three things equal to each other? So this is called the symmetric equations for the line. It's a neat little move, and gives you a point tester out of a parameterization. Okay, so we're going to move on now to section 1.3. Oh, we only have 5 minutes left. The thing about it is, again, the dot product, it's pretty much review. I think y'all have seen most of this, if not all of this before. So I'm just going to hit what I think are the most important things. I'm fairly sure you already know the formula. Quick reminder, there's a bunch of properties of dot products. They're in the book. Make sure to review those. A little bit of terminology I feel the need to point out. A lot of people and contexts will conflate these two terms. I think that's unfortunate. They're a little bit different. Perpendicular is a geometric concept. Two directions are perpendicular to each other if those directions have a 90-degree angle between them. Notice how geometric that was. Directions, those are geometric things. Angle, geometric thing, right? So perpendicularity is a geometric concept. Orthogonality is an algebraic concept. Orthogonal means the dot product 0. Now, of course, y'all know from Math 218 that, wait a second, if they're perpendicular, the dot products, aren't these the same? What's the difference between these? It's tempting to wonder. The difference boils down to, what if we have the 0 vector? And of course, if you have the 0 vector, the dot product will definitely be 0. So they're definitely orthogonal. 0 is orthogonal to everything, but the 0 vector doesn't really have a direction, so it's not really perpendicular to anything. So if one of the vectors involved is 0, then you have, yes, orthogonal, but no, not perpendicular. So slightly different ideas. Be careful about the use of these terms. I'm afraid that our book is a little bit, well, anyway, the book uses these terms more interchangeably than I would prefer. I'll say that. So I would like y'all to be more careful and use these like this. Okay, really quick. I know y'all remember this formula for the unit vector pointing in the direction of a given vector. Right, the unique unit vector pointing in a given direction. Just divide a vector by its own magnitude. Standard move. And a little bit of trig allows us to compute this thing called a component. Component being, given a vector, and if I want to know to what extent does that vector point in that green direction being defined by some other vector, v. Right, so the v component, we say, of the w vector, that component is defined to be that distance. And you'll notice that is one of the sides of a right triangle, and you can write down a little bit of trig, and here it is. The trig of this triangle is that. You can literally straight up solve for a component in that formula. And then you do this little move down here where we divide and multiply simultaneously by the same thing. Perfectly legal. Right? I just multiplied by 1 here. I multiplied and divided by the same thing. Perfectly legal. And that little slick move allows me to rewrite that numerator as a dot product, which is easy to compute. So it's a very cool little calculation. A nice punchline. Let's see here. Nice punchline is that components can be computed with dot products. And here's an even better version, in my opinion. This is just my own personal opinion. But I like to point out, check it out, we have there v divided by the magnitude of v. That's, again, that unique unit vector pointing in the direction of the given, the initially discussed, trying to figure out, component in the direction of v. This is the unit vector pointing in that direction. So altogether then, components are computed as a dot product with unit vectors. It's a really, really nice little formulation. Dot product with the unit vector is how you compute a component. Very convenient. Okay. Super quick last little thing. I have to throw a couple of quick words at it. The projection looks very similar. The difference between a projection and a component is just that the projection is a vector. And so in order to write down the projection, we just have to say, well, sure, we know what this distance is. We know what the component is. The component is this formula right there. We just got through computing. To make it a vector, we just multiply by the unit vector u in that direction. And the projection then is that vector. That's really all I need to tell you about projections. Now, the book has a slightly different point of view. I think this is the easiest way to think about it. Right? If you want to describe a vector, if you know the magnitude, you know the direction, unit vector direction times scalar magnitude will always give you that vector that points in that direction with that magnitude. So I think that's the easiest way to write that down. If you like the book's point of view, it's this. Take your pick. I like mine better. I find this one a little uglier, but it's equivalent. Okay, we made it. Believe it or not. So we're done with 1.1, 1.2, and 1.3. I'll edit the syllabus lecture schedule accordingly. All of that's going to be due on Friday. Y'all have a nice rest of your day. See you later.
Thank you.
Yeah, no problem. Okay. Yeah.
What time on Friday do they usually do?
Oh, yeah. It's 11 p.m. Always 11 p.m.
My own question.
No problem. No problem. Okay. Hey, what's up?
I was wondering if you record lectures while you're talking.
Oh, yes, I do.
Upload them
And
as well.
thank you. I forgot to stop the recording here. Let's